Alright, so this problem is not going to be a straightforward, easy problem. In fact, you're not probably going to get anything this complicated, but it's going to point out a number of possible complicating factors that they could throw at you. So it's kind of a catch-all for a bunch of things. First of all, is we have we have 5 torques, well, 5 forces, I should say, acting on this. But not all of them are going to produce a torque. So the first thing we look for, are there any of them that are directed so that their force is going to point right through this axis of rotation, which is right in the center of the object? And the clearest one is right here. It's located 1.5 up, it's perpendicular to this side of the rectangle, so yes, this one is not anything we have to worry about. There will be the torque produced by 5 will be nothing because it is directed towards the center. All right. So there's that. We got rid of that one. Are there any others that look like they might do that? Well, okay, so if you see my little dotted line, you can see that was probably my intent. But here's how let's say you didn't have the dotted line. I need to know, let's see if I can work in a different color here. I should probably go colored pencils. Let's see. So what I need to know is if this is on that line, then this angle here will be the same as that angle there. If these two are equal, then that means this is all just one straight line. So I got to find that angle, but we can do that. Little right triangle here. This right here is 0.15. It's half of the side. Notice the sides are 10, 20, 30, so it's 0.3 this way and 0.8 this way. This is 0.1. And so if I want this angle, I'm going to do the inverse tangent of the opposite, 0.15, over the adjacent, which is 0.1, to get that angle, the red angle. And if I do that, I will in fact get 56.3, which is my proof that this force is directed right towards the center. And therefore, torque by 4 is also 0. I think it's pretty clear on inspection that 1 is definitely not passing. The line of its force is not going through the center. Neither's 2, and neither's 3. So those are going to produce torques. All right. So we know the forces. What are the lever arms? What is the R value for it? Well, they are literally the distance from the center of the axis of rotation. So for example, for force 1, its R value is this line. It's the distance from the center of rotation to where it's applied. Okay, great. We got to find that. And we also have to find, I know this says 90 degrees, but that's not the angle it makes with this R, and that's what we need. So let me erase that if I can. I think I can. Let me erase that 90. It's nice to know that it's perpendicular to that side, but what we need ultimately is either, I'm going to do a dotted line out here, either this angle or this one, but some angle between the force and the R. So let's first find, just make a right triangle. Here's a nice right triangle. So let's see if we can find R here. Well, this is 1.5. And this is 0.1, 0.2. This is 0.2. Just counting over. All right. So this Pythagorean theorem should give us that. It's going to be 1.5 squared plus 0.2 squared. And then take the square root. And I get 1.513. So R for 1 is 1.513 meters. Meters. I got to be careful. I'm mixing meters and centimeters. This is correct. This should be 0.15. So it's just, and it means I'm going to be off a decimal point, I think, here. But let's see, 0.15 squared plus 0.2 squared. Yes, that was close. That's going to come out to be nice and easy, 0.25. My apologies. So R1 is equal to 0.25 meters. That's this distance right here. Now, we need an angle here. We either need this angle, which would be the same as this. That might work. Let's do that. So this angle here will be the same as this one here. If we zoom in on that, I'll try to show you that. So the angle between the force and the line of R right here is the same as this angle of that triangle. And if I can find that angle, I'll know that. That's an angle between the two. It'll work. So this angle, opposite, adjacent. So we can use the inverse tangent. So second tangent of 0.2 divided by 0.15. That's a 53-degree angle. 53.1. So we should be able to use that angle for theta. That would work. Really, either of these angles will work. We'll use the acute one. It should work. All right. So there we did all that for here. So we have just off to the side. We'll just jot this down. We'll even do it in green since that's what we seem to have there. So off to the side. I'm just going to make a note to myself to clean things up. I've just discovered that the torque by force 1 is going to be an R value of 0.25 meters times a force of 3 newtons and the sine of a 53.1 degree angle. So this is all what we have to do to find torque 1. So now we got to do the same for torque 2 and torque 3. Let's go with got red for that. We got green for that. Let's go with like a bluish color, I guess. So for torque 2, this is my R, that distance. So we'll have to calculate that. But I think we have a shot at that because this right triangle will help us. And we'll need to know, really what I need to know is this angle. Because if I can get that angle and add it to this one that I'm given, that will tell me the angle between them. So this angle is the same as this one. So let's get our sides. This is 0.15 and this is 0.4. That gives us a hypotenuse using Pythagorean theorem of 0.4 squared plus 0.15 squared equals second square root. Alright, so that gives us an R value here of 0.427 meters. That's R. Now I want this little angle right here. Well, opposite and adjacent is tangent, so I'm going to say the second tangent of 0.15 divided by 0.4 equals 20.6 degrees. Ah, wait a second. 20.6 degrees. Well, that's 20.6 degrees, and I add it to 69, so that's 20.6 plus 69.4. Well, that's a 90-degree angle. What do you know? So it turns out that this, the angle between the force and the R, the lever arm, is 90 degrees in this case. So that's good, because that means we have, for that one, we'll do it down here with this other one. So I now know that the torque by 2 is a lever arm of 0.427 meters times a force of 9 newtons. And I don't really need to worry about the sine because the sine of a 90-degree angle is just 1. So I straight up. Alright, so let's take a look at this last one. We'll give it a shot in orange. We'll see how it comes out. So we need its R. Alright, the good news is its R is the same as the other ones. Alright, it's just the diagonal from here to here. So it's going to be the same distance. 0.427 meters. Sweet. And of course this is still 0.15 and this is still 0.4. And that means this angle here is still the 20 point, I believe it was 20.6. So this angle here is 20.6. I have to add that to 90 to get the angle, or if I wanted, I could extend this past and I could try to figure out what this is. That would work too. That's the acute angle. So let's see, if I have 180 would go from here all the way to here. And if I take 180 minus the 20.6 minus 90, I get a 69.4 degree angle. So this right here is 69.4 degrees. I guess I could have figured that out. But that is the angle between the lever arm, the line of the lever arm, and the line of the force. So for torque 3, I have a lever arm of 0.427 meters. I have a force of 11 newtons. And I get the sine of 69.4 degrees. Alright, those are my 3 torques. Complicated, but there's a lot there. Points out that R, your lever arm, is from where the point where the force is applied to the axis. The angle you'll have to figure out. Doesn't guarantee that the angle is always 90 degrees like it was here. In fact, sometimes it might look like it's going to be, but it isn't. Because this at 90 degrees to this line, this is not to the center. It's got to be to this one. So there's a lot of stuff there. Gone through, we find it. Okay, now, considering this is the axis, which way is this one rotating it, trying to rotate it? So if there's nothing else involved, this would try to rotate it this way, right? That'd be positive. Just make a note of that. This would certainly try to rotate it negative. And this one would try to rotate it positive. So, if I do my expression down here, so first of all, net torque is equal to I alpha. We'll come back to that. I also know that net torque is equal to, let's see, we'll do torque 1 plus torque 3, they're both trying to go counterclockwise, minus torque 2. But we have numbers for all these, or we will. So we'll find the net torque by calculating each of these over here. So let's take a second to do that. For torque 1, it's 0.25 lever arm times 3 newtons times the sine of 53.1 degrees. And I get 0.5997. So let's just call it 0.6 Newton meters. For 3, I've got 0.427 times 11 times the sine of 69.4. 4.396, so we'll go 4.4. So plus 4.4 Newton meters. And then 2 is going to be just 0.427 times 9. Because it was at a 90-degree angle to the lever arm, it doesn't have to worry about the sign. So it is 3.843 Newton meters. So what's our net torque? Watch me pick numbers where they all come out to be 0. Be my luck. Let's see. So now and then, so I'm going to go plus 4.4 plus 0.6. All right, so I get a positive 1.16 Newton meters. So these two are outdueling this one. This one gave a good fight because it didn't have to worry about, all of its torque was perpendicular. But so this is my net torque. Okay. What's I? Well, nobody's going to make you remember I for this one. It turns out, if you look it up, the I through the center of a rectangular plate is this. So let's take a second and figure out what that is for our situation. I haven't actually given you the mass of the plate. We'll make up a number for the mass of the plate. But it's going to be, the I in this situation is going to be 1/2 or 1/12. I'm having a moment of doubt. One moment. It is in fact 1/12. So it's going to be 1/12 of the total mass of our plate. Let's say our plate is pretty massive. Let's say if it was steel and it was that big, it'd be at least, like, we'll say 3 kilograms, depending on its thickness. And then it's length squared plus its width squared. So the length is 80, we'll say, so it's 0.8, because that's in meters, squared plus 0.3 squared. So this is going to be our value for I. Once again, you're not going to be expected to memorize this. They'll either give you this equation, or they'll do all these calculations behind the scene and just give you the number. But it's not hurtful to see where it comes from. So we're going to go 3, well, let's do the parentheses first. So let's go 0.8 squared plus 0.3 squared, get an answer. And then times 3, and then divided by 12. 0.1825. So our I value is 0.1825. It is a property of the plate, and it would be in kilograms times kilogram meters squared. That's I. Alpha is what I'm looking for. I know the net torque now is 1.16 Newton meters. And so alpha is going to be 1.16 Newton meters, the net torque, divided by the rotation, the moment of inertia, 0.1825 kilogram meter squared. And we get 1.16 divided by angular acceleration of 6.4 radians per second squared. I suppose we should, what the heck, we've done everything else complicated. How do the units work out? Well, Newton times a meter, so that's a Newton is a kilogram meter per second squared. But if you multiply it by a meter, so it's really a kilogram meter squared over second squared. And then you're dividing it by a kilogram meter squared. Wait a second, that means you got a 1 over a second squared. If you recall, radians are actually a unitless quantity, so this makes sense. You can put radians in there because that helps you understand what it is, but this is the way the units should come out. Alright? So you're not going to run across one this complicated, but if you could follow along and understand why these torques are what they are, and how these angles all interplay, and why these lines are what's important, that's pretty good. If you understand that there's an equation for every type of shape, and I went up and found this one, that's pretty good. So yeah, if you could follow along on this and see that there's some important things there, just keep in mind that not everything is a solid bar with everything pointing at it perpendicularly. Keep that in mind.